All right. So in this case, let me introduce myself. So this is the overview about myself actually. My name is Noor Asma Fazli bin Abdul Samad. So I will serve as your instructor for this class. So in this case, a little bit academic qualification from me. I got degree and master in chemical engineering from UTM, Johor. And then I pursue my study in the process modeling and control area at Denmark Technical University, DTU. And lastly, I also extend the study in the postdoctoral area around the properties prediction. So this is my contact number. You can reach me through this email, asmafazli@ump.edu.my, and my room number 8305. So this is located at the Chancellery building. So since this semester we're supposed to have the hybrid mode of operation. So although the third year is not compulsory to come back to UMP, however, if you are available in UMP, you are free to see me for consultation. Just inform me through my WhatsApp number. So this is my phone number. So you can contact to me. And let's say if you want to discuss something, then feel free to do it. My WhatsApp number and my office number. So in this case, for the sake of the communication, I already set up the WhatsApp group. So in that WhatsApp group, I will share some latest information regarding the process control subject. For example, the notes, the exercise, the tutorial, the date for the test, or any relevant material will be shared in the WhatsApp group. Of course, we also have the Google Classroom, where in the Google Classroom, I will load all of the necessary learning activities to all of you. I hope you already joined that Google Classroom. And for this course, I would like to emphasize on the course assessment. So for this course assessment, we divide it into 4 different items. The first one is the assignment, which carry around 10%. So this assignment normally is based on the group assignments between 3 to 5 members per group. So normally for the assignment, we will cover the drawing, piping and instrumentation diagram, PNID. Where PNID stand for the piping and instrumentation diagram. So what is mean by PNID is about the control system. Let's say we want to control single unit operation. What is the variable that we want to control? Is it temperature, pressure, composition, and so on? And how the drawings looks like. So this will be covered in the assignment, which carry around 10%. And then we have tests. Tests will carry around 15%. So in this case, I already made a survey in our WhatsApp group, where here the test will be conducted on the 15th April 2022. So today is 14 March. So that means there will be 1 month to go before test. So this test will be conducted online at around 8 p.m. to 10 p.m. It will take around 2 hours, and there will be 2 questions which will cover the chapter 1 and chapter 2. for this subject. So the test will be conducted individually. So this one will be standalone mark. And lastly, for the coursework is about the project where you will perform dynamic simulation. We will use MATLAB software. So in the project, you will use the MATLAB software in order to perform the simulation. So here, the project will be assessed based on the group. So this group still consists around 3 to 5 members per group. And this will carry around 15%. And lastly, about the final exam, in this semester, we still stick around the 60%. So this means a lot of the weightage is for the final exam. So this will determine the overall performance of your understanding towards this subject. So that is the course assessment for this subject, which consists of the assignment, test, project, and final examination. Any question regarding the course assessment? Okay, if there is no question, then we go for the textbook, the main reference that will be used for this subject. So you are free to use any kind of the textbook. However, the main thing that we will refer is based on this textbook, which is Process Dynamic and Control. So there are so many versions. The first one is the second edition textbook. So this is one of the textbook that you can use. And this one normally for the second edition is a complete version. Complete version. That means when we say complete, it's cover everything. All of the content that is covered in this subject will be available in this textbook. And the good thing about the second edition is support with the explanation. That means any kind of the exercise, any kind of the material is supported with the theoretical and discussion. So this second edition for me is the good textbook for all of you. And then if you prefer, you can also use the second one, which is based on the third edition. Still the same textbook, only the different version. Where here you can see this one is for the international student version. So meaning that when it's referring to the student version, it got simplified. So some of the exercise, some of the explanation is simplified to be suitable for student understanding. So for this textbook, you also can refer it, no problem. As long as you have the copy of it or you have the hard copy for it, you can use the third edition. And for the last textbook, the latest edition, which is the fourth edition, Process Dynamic and Control Techniques. This is the latest version, where in this latest version, they emphasize on the techniques. That's why you can see the word techniques on the topic, on the title. Before this is just Process Dynamic and Control. But in the last or in the latest edition, it's include the technique. So that means it's include or it's emphasized the technique used to solve the process control problem. However, in this case, based on my experience, based on the last subject and so on, this textbook sometimes lack of the formula. Lack of formula and related table. Although it can be used to refer as a textbook, sometimes some of the information is not included in the latest textbook. So meaning that if you have this copy of textbook, you need to have the additional formula or table from the previous textbook. So in my opinion, among all of these textbooks, the most suitable one that I recommend for you to have is the third edition. This textbook in the middle. If you have the copy of this textbook or you have the real textbook for this part, then it should be okay. You don't need to copy any kind of the formula. It's suitable for you. It's not too complicated. So this is the textbook that will be used for this subject. In my case, normally during the teaching activities, I will refer to the third edition textbook. So I will use this textbook for any kind of the material or exercise. So this is the textbook for this subject. Any question? Okay. So in this case, before I begin our class, so let's hear some opinion from all of you, from any of you regarding this subject. Any opinion or maybe any input from all of you, from any of you regarding this subject? What do you hear from your senior, or what is your past experience about this subject and so on?
Doctor.
Yes.
May I ask a question? Is the textbook is compulsory for us to buy?
Okay, since in this semester we still conducting online mode, so you don't need to buy. As long as you have the soft copy, then it is enough.
Oh, okay, understand, doctor. Thank you.
Yeah. Compulsory to have the soft copy. If you have the textbook, the hard copy, then it will be more easier for you to study. But it's not compulsory to buy the textbook. So any other input from all of you, from any of you regarding this subject?
Okay.
Okay, no Amira Farah Shasha. Susah. Alright, susah. Okay. Just for your information, last semester is the first time we were conducting this course. Particularly for the final examination is carried around 60%. Okay, for your information, last semester when we were first conducting this subject, I think around 30% of the total student fail this subject. Because normally before this we have the additional 20% which cover for the quiz or assignment that is easily scored by the student. But last semester, they don't have that kind of luxury. That's contributing to the low grade among the student. However, just I would like to emphasize, last semester also, we have around 3 students got the A grade. So when we have 3 students got the grade of A, then meaning that this one still possible to achieve a better grade. It's still doable. The advantage of this semester, normally you already have the past experience. That means you know how the question looks like. So you can refer to the last semester question and then you will determine or you will adapt the difficulty level of this subject. So for me, in this case, how to get the better grade is to have the active participation. So you need to show your participation, because here we don't have the mark or we don't provide the mark for the exercise and so on. The main thing based on the last semester, what I can observe is whoever student did the exercise, have a discussion with me, then they will get a good grade. So I expect also the same initiative from all of you. I will give the exercise and you also need to do your job. Do the exercise by your own. Do not simply copy and paste from your friends, because for me sometimes it is meaningless. You need to test your ability by trying doing the exercise, and let's say you unable to answer it, it's okay. So you know where is your weakness. So this is the thing that you can further improve later on. If you just simply copy and paste from your friend, then you submit to me, then I will assume you understand the subject. So that is the thing. You need to be honest with yourself. It's not about the getting all of the question correctly. It's about your understanding. So normally, process control is one of the killer subject in the chemical engineering. That is the common thing. If you observe from other university, from UTM, from UM, from USM, still process control dynamic is considered one of the tough subject in the course. So there is it's unavoidable. But in the end, it's still doable to get the better grade. I'm here to help you to get the better grade, and if you are committed to get the good grade, then for sure I will be here to assist you. No problem. Okay, let's take a look on the topic, the introduction. So this is the textbook, the second edition. All right, now we go for the introduction. So here we go straight away for the case study. So we don't dwell about the introduction so much. So let's see. In this case, a blending process. So here you have the term blending. So what is meant by blending? Blending is what we call it a mixing. So meaning that you have two components you want to mix into single component, or you want to achieve uniform composition. So for this part, two streams, 1 and 2. So you have two streams coming into the system. Two stream 1 and 2 are being mixed in a well-stirred tank. So this is the first sentence. stream 1 and 2 are being mixed in a well-steered tank, producing a product stream 3. So this is your stream number 1, stream number 2. You add it together and then you have the stirrer. So this is your stirrer. The function of the stirrer in this case is to have or to ensure you have a good mixing of the composition. So meaning that when you mix it, in the end you will achieve what we call it uniform composition. So once you complete the stirring process, you achieve the uniform, you will exiting the process at stream number 3. So based on this, you have 2 inlet and 1 outlet. Okay, each of the 2 feed stream. So each of the 2 feed stream is composed of 2 components, A and B. So in the stream number 1, you have A and B, and stream number 2 also you have A and B. Let F1 and F2 be the mass flow rate. So F1, F2 is the mass flow rate, kilogram over minute, the unit is the mass over time, and T1 and T2, their corresponding temperature. So for this part, since you want to mix it, it needs to involve the composition. So S1, SA1 and XA2 are the mass fraction of the component A at the inlet stream. And then F3 and XA are the mass flow rate and mass fraction of A in the outlet stream. So here the elaboration of variable. So first we have the unit operation. The unit operation in this case is the blending tank or stirrer tank or mixing tank. So you put 2 flow rate coming into the system, you mix it and then you achieve the composition. So based on the process description, here we identify what is the variable involved. So based on this, you have the flow rate, mass flow rate from the stream number 1 and stream number 2. And then based on the mass flow rate, you also has the composition in the form of mass fraction. So you have the mass fraction in the stream number 1, stream number 2, as well as the stream number 3. And lastly, in this case, it's mentioned a coil is also immersed in the liquid of the tank and it is used to supply heat to the system with steam. So this is your coil. So when we put the coil inside the tank, that means it will provide the heat. So this heat in the end influence your temperature inside the tank. So meaning that for this part, the temperature will be changed. So that means what we can observe in this case is the temperature change, the mass change, the composition change. So if we take a look further, the diagram again, if you recall this subject represents the process, dynamics, and control. So this is the name of this subject. The first term that will be used is the process. So what is the definition of the process? Anybody? The definition of the process?
A series of reaction
A series of reaction.
which we will get the product the desired product.
Okay, thank you very much for your answer. So in this part, actually when we have the process, of course you will achieve the product. So in order to achieve your product, you need to supply it or to feed it with your raw material. So in the other way, the process means how to convert your raw material into product. So this is what it means by the process definition, where process itself is the conversion of raw material into product. So when we reflect the given case study, your raw material is coming from your input. So normally the raw material itself is considered as your input. So that means you put the flow rate coming into the system. So that is your raw material. And then you want to mix it. You want to mix the solution. And then by mixing the solution, you will get the desired product in the form of the composition. So that is what is meant by the process. So for this part, the process understanding is very important. Why is important? Because it decides what variable that will be involved. So let's take a look. So here you have the stream number 1, stream number 2, and then stream number 3. When we have the F1, where this one is stand for the mass flow rate, F2 is also the mass flow rate. You have the mass flow rate coming into the system. It's entering the system, entering the system. So when you have the mass coming into the system, then it will change your volume inside the tank. So this is your volume inside. The V here stands for the volume. Just to imagine, to have the understanding, let's say we have mass flow rate here 5 kilogram per minute. The second stream 3 kilogram per minute. And then the F3, let's say here you have 2 kilogram per minute. You have 5 and 3 as the inlet flow rate, and you have 2. What happened to the volume?
Increasing
Why it is increasing?
because the input is larger than the output.
Yeah, correctly. So in this case, you have, normally when you try to visualize the dynamic behavior of this process, you will consider what we call it the simple mass balance, in equal to out. The one that you learn during the material and energy balance subject. When you have the in equal to out, here you can see the in is around 8, the out is around 2. So you have input larger than your output value. So when you have this one, that means more liquid coming into the system and less liquid exiting the system. This will contribute to the increment of your volume. Volume will definitely be increased. How much it increase? This will be observed through the mathematical model. So that means you need the mathematical equation in order to observe how the behavior of the volume is changed. So this means in this case what I want to emphasize by evaluating the impact of the variable, then we need to come out with the relevant mathematical model, where this mathematical model will give us how the behavior looks like. So in this case, we can say that volume is increased, but how much it is increased? That can be determined through the mathematical model. The same goes with the composition here. You have the SA1, you have the SA2. And then in the end, you have the XA. So when you try to make something, let's say in this case, I just give the random example, random value for you to imagine. Let's say SA1 here 0.5, you have SA2 0.9. So meaning that when we try to mix it, then you will have or you will achieve a new composition. So that means there will be a change of your composition value. So how it is changed? It will depends, or it can be predicted using mathematical model. The same goes with the temperature. You have the T1, you have the T2, you have the T, and then you have the Q here. Let's say here T1 at ambient temperature 25 degrees C, T2 also 25 degrees C. Then you put heat. So this heater maybe you put it 1000 kilojoule per hour or per minute. So you heat it, then of course the temperature will be increased from ambient to the higher temperature. But what is the value of the higher temperature? How we can determine it? By using mathematical model. So for this case, we can see that the volume, the composition, the temperature, this variable will be changed. How to observe the change of this variable? Then you need the relevant mathematical model. And how the mathematical model can be generated or can be derived is by looking at the conservation of mass and energy principle. So this is the extension from what has been learned in the material and energy balance. In the material energy balance, you don't consider the rate of accumulation. For example, in the conservation of total mass, the general equation in this case is rate of mass accumulation. How much your mass is accumulating in the system equal to rate of mass in minus rate of mass out. So in the mass balance subject, you don't consider the rate of mass accumulation. That's why you get in equal to out. So you just need to do the balance based on the rate of mass coming in with the rate of mass coming out. That's all for the mass balance. However, in this case, since we consider the rate of mass accumulation, that means you need to consider the change of time. So when you consider the change of time, that means, let's say here, right now is 12:39. So what happened to our level in 5 minutes? Around, let's say, around 1 o'clock, what happened to my level? It's increased how much? So from 12:39 to 1 p.m., you have the time change. The time is moving based on its trajectory. So this is what we call it dynamic. When you consider in equal to out, you don't consider the rate. Then this one is referring to the steady state. where delta T normally is 0. For this subject, however, we will consider the time difference. And you want to consider the time, then it is referring to the dynamic. So that is why, in this case, you can see why the subject have the dynamic term. First, the process. You understand the process. You know what is the variable involved, and you can predict which one can be changed. And then the second term is the dynamic. In the dynamic, you put the time different, you put the interval of the time, and then you see how the behavior is changing. Like I said before, let's say the temperature is changing, how much it is changed? Is it linear? Is it steadily? Is it ramp? So this will be determined through the conservation of mass principle. So in this case, we will consider the rate of accumulation, where this one is equal to the rate of mass in minus the rate of mass out. And since you have the composition change, the mass fraction will be changed, then we also need to consider the conservation of component. For example, in the given case study, you have two components, A and B. Then that means we will evaluate or we will derive the equation to represent composition of the A and the composition of B. Once we obtain the model, then we can observe the behavior of change for these components A and B. So for the conservation of the component, normally we will start with the rate of component accumulation, the first term. And this is account the rate of component in minus rate of the component out. How many this component entering the system minus the how many of the component exiting the system. And some of the term that can be included is how many the rate of component I produce and how many it has been consumed. So in this case, you can see there are 4 different items on the right hand side. Component I in, component I out, component I produce, and component I consume. So the selection of the component here, or selection of the term that need to be used, depending on the either your process involve the reaction or not. For this part, the blending system, you just mix the composition into one. So when you mix it, then it does not involve any reaction. You just mix A plus B. You get new composition A plus B as well. Only the composition will be different. There is no component involved. No new component produced. So when there is no component produced, that means there is no reaction. So no reaction, that means you don't need to use this one. You just involve the component I in and minus the rate of component I out. In some cases, this is what we call it no reaction involved. No reaction, no component produced, no component consumed. In some cases, you have the A plus B, you get C. A plus B, you get C. So this is where the reaction involved. You produce a new component here, C. In the inlet, you have A and B, but during the process, you generate a new component. Then you will consider both terms, rate of component I produce minus the rate of component I consume. That is the term that will be accounted in the case of the reaction process. And lastly, what we want to cover is the conservation of energy, where in the energy is normally is referring to the temperature. So the energy in this case we assume is based on the enthalpy. So normally for the energy conservation, it is developed on the principle of the first law of thermodynamics, where the energy cannot be created, cannot be generated. However, it can be transformed from one form to another form. So how it is transformed? Then in this case, we accumulate the energy based on its rate, and we account it based on the rate of energy in by convection, out by convection. So you have the stream coming into the system, you stream exiting the system. So this stream coming into the system carries some energy. This energy is bring together by convection, and is exiting also the system by convection. So this is contributing to the energy change in your system. And then sometime for the case of net rate of heat addition to the system from the surrounding. So this normally is based on your Q. This Q is coming from the coil. So you put the coil, this coil provide additional heat into the system. Before this, rate of energy in coming from the flow rate. Flow rate in or flow rate out. But for the net rate of heat addition is coming from the coil. Let's say you don't have coil, then you don't have the heat addition. And lastly, the net rate of work performed on the system by the surrounding. So this is what we call work shaft or shaft work. So normally this part we just neglect it. There is no work involved for the system. So for this subject, normally we neglect the effect of the work. We simplify the process, just accounting the rate of energy in and out as well as the net rate of heat addition based on the coil. So that is the principle of the conservation of mass and energy. So any question? Just to be clear, this equation will be used frequently in this subject. So I hope you get familiarized with the term. Whatever you do in this subject, we will definitely use all of the conservation equation. Although it looks like simple, sometimes it can get complicated. So this is where we need to make sure you're fully understanding on the concept. So I open to any question that you may have before we go further. Akif ada kat sini? Akif.
Ada doktor.
Kat mana Akif?
Ha? Dekat mana? Dekat bilik ada.
Okay, alright. Saja just checking on you. Anything, Akif?
No, doctor. Okay, sir.
Okay, how about Kevin? Kevin Wong.
Yes, doctor.
So how about you? Any comment so far?
No comment, doctor.
Okay, all right. Thank you for your response. Usually, I really like to have some interaction with all of you. That's why I'm asking the name. So, but please don't be afraid. It's not that I want to punish you. So, any other question before we take a break?
Doktor,
Yeah.
yang call ni kan doktor, yang Q tu,
Yeah.
kalau soalan tak mention ada call tapi temperature berubah, so maksudnya Q masih ada ke?
Okay. Thank you very much for your question. Alright. Let me demonstrate you a little thing. So in this case, the question asks about the case study. Let's say I draw it a little bit. Alright. For this part, it's clear. For the case study I give it to you, it's clear. The Q is there. So that means you have the heat addition. You have the coil. In some cases, when you read the question in the test or final examination, it does not mention any coil. It's like this. So no coil involved. How about the temperature? So the temperature normally depends on the value of your inlet. Let's say here you have T1 25 degrees C. T2 also 25 degrees C. So you miss it. Normally in this case we assume the temperature is not going to change. Because here we normally neglect the heat of vaporization, the heat of the formation and so on. We neglect it. We just assume whatever the temperature coming from the flow rate only. So when you have inlet temperature 25, the second inlet temperature is also 25, then we can assume the system is isothermal. When the system is isothermal, no temperature change. You don't need to do the energy balance. However, let's say you have second condition. The temperature T1 is 25 degrees C. The temperature T2 you have 100 degrees C. So you have two different temperature coming into the system. Of course, in the end you will have the temperature change. So in this case, you cannot assume it as isothermal. So if we just to calculate further 25 degrees C, 100 degrees C, maybe in the end you will get around 50, 60 degrees C. So there will be a temperature change inside the tank. So you require the energy balance for this part. Although it's important to know that in this case you don't have any coil. So in other words, if you don't have the coil, then that means you need to check your inlet temperature. Is it constant or not? If the temperature inlet has the same value, then you don't need the energy balance. You can assume it as isothermal. If the temperature inlet like this, 25 degrees C and 100 degrees C, then of course you will have a temperature change inside the tank. So that is the answer for your question.
Doktor,
Ya.
maksudnya ada Q lah kan?
Tak ada Q.
Oh,
Ada
tak
T saja.
Oh.
Sebab dia tak ada coil. The Q is coming from the coil.
Alright, thank you doktor.
Alright. Now we take a break before we start doing the derivation. Okay, let's continue with the derivation of mass principle. So we will use the given case study. In this case, we have the blending system where you have two inlet coming into the system. So for this part, the F is your mass flow rate. Where the unit of the mass flow rate given is the kilogram over minute. And the X is the mass fraction. The unit of the mass fraction normally, since you have the mass in the kilogram, so the mass fraction should be kilogram over kilogram. So this is the standard unit. So you need to just to ensure you have the consistent unit. Let's say mass flow rate you have kilogram, then mass fraction needs to have the kilogram over kilogram. If you have the gram over gram, you need to convert it into kilogram. Because here the consistency of the unit is very important. So here, based on our observation of the process, when you have two flow rate coming into the system, one exiting the system, the volume inside will be changed. Either it's increased or decreased, is depending on the value of your mass flow rate. So now we want to obtain or to derive the relevant mathematical equation to represent the volume inside the tank. So based on the conservation of total mass, the first equation is the rate of mass accumulation. So in this case, the rate means based on this is based on the d m over dt, where d is the derivative, the differential equation to account how the mass is changed against time. That's why you start with the dm over dt, where the m stands for the mass. So in this case, since your unit is kilogram, then mass is kilogram. And your dt is your time, which is, in this case, is in the minute. So you have the m over dt to represent the rate of mass accumulation. And then equal to rate of mass in. Normally, the rate of mass in has the following symbol. M dot in minus M dot out. M dot in, rate of mass in. M dot out, rate of mass out. So this is the standard symbol that will be used to represent the rate of mass in minus the rate of mass out. So based on this, we know that the dm dt equal to m in, the rate of mass in coming from the stream number 1 and stream number 2. This is the mass coming into the system. Since we need to ensure the unit is consistent on the left and the right hand side, meaning that for this part, the rate of mass out must has the unit of kilogram over minute. So when you have the kilogram over minute on the right hand side of the equation, it's also tally or consistent with the unit in the left hand side of your equation. So based on this, you have two flow rate coming into the system. So here you need to add F1 plus F2. So this F1 plus F2 represent the rate of mass coming into the system. And then you have minus F3. The F3 is the rate of mass exiting the system. So that's how you can adjust accordingly. So when we try to check again, this one, the dm over dt, you have kilogram over minute. And the right hand side, also kilogram over minute. Then it is consistent. So this represents your conservation of total mass. The problem here is your left hand side, the dm over dt, change of mass against time. In this case, if you take a look on your case study, the process given, the unit or the variable used is volume. So we need to identify what is the relationship between the volume and the mass. So this normally we can use density to relate the mass and the volume, where the mass normally m equal to density multiplied with the volume, where the mass is kilogram, volume is meter cube, and the density is kilogram over meter cube. So you cancel meter cube, you get kilogram. So that means this relationship can be used to relate mass and the volume. So what we need to do with this relationship is to put this relationship inside the question. So that become the d rho v over dt equal to f1 plus f2 minus f3. So what happened next is to expand the equation, where here the d rho v dt, we can expand it become rho dv dt plus v d rho over dt. F1 plus F2 minus F3. So based on the expansion of the density and the volume, you get two additional terms. The first one is the rho dv dt. And the second one is the v d rho over dt. So we have the density relationship. In this case, the first term, volume change against time, dv over dt, volume change against time. So that is reflecting how the volume inside the tank is changing. And the second term is the density against time. So for this part, normally the density is not going to change against time. It's fixed. If we try to imagine, the simple way is to imagine the density of water. Today, its density of water is 1000 kilogram per meter cube. What is the tomorrow density of water? Anybody?
Still one.
Still the
Same.
same, right? 1000 kilogram per meter cube. Meaning that if you refer to the tomorrow density, it's still the same value of today. The density is not going to change. But the value of density is not going to change. So if it's not changed, or in other words, it's constant, then this means this part will become 0. Why the d rho over dt can be neglected? Because normally the density is not going to change against time. That's why we can simplify it to become d rho over dt equal to 0. Any question on this? Any question?
No question, doctor.
Okay, thank you for your response. So we complete the conservation of total mass, where based on this, your equation reduced to rho dvdt equal to F1 plus F2 minus F3. So this is the final overall mass balance for your given system. Where right now, you already use the volume inside the given variable for this case study. So once we already complete the conservation of mass, then we can focus on the conservation of component balance. So this is your equation, conservation of component. Now we concentrate on this part.
Doctor,
Yeah.
your voice is lagging.
Oh, my voice is lagging. Oh, sekejap.
Yes.
Okay. So in the previous case, we already developed the conservation of total mass. Boleh dengar? Can you hear me?
Yes, Doctor. Can.
Yes,
Alright.
doctor.
Boleh.
So for the second part will be the conservation of the component. The needs of the component, because we deal with the two component involved in this case. So for this part, we concentrate on the XA. As given in the problem, you have the SA1, SA2, and the XA here. So we want to develop the component balance of A. For this part, normally we employ the conservation of component principle, where in this case you have the rate of component I accumulation. The component I referring to the component A. So the component A here, we start with the rate of component I accumulation, still the same principle, where you start with the D M A over dt.
Doctor,
Yeah,
your writing is
excuse me.
doctor, your your writing is not visible.
Oh, you cannot see my writing.
Yes, yeah, doctor.
No.
No.
Okay. All right. So for this part, we focus on the component A derivation, where we use the conservation of component I conservation principle. The first part is the rate of component I accumulation. So for this, we focus on the component A, where the rate of component I accumulation is represented by dMA over dt, where the MA here represent the mass of A. Mass of A. Before this is just total mass. So for this part, we specifically focusing on the mass A. So this means the unit for the mass of the A must be kilogram A, and the dt is the time, which is in this case is referring to the minute. So you have the dMA over dt equal to the rate of component I in. So based on your case study, you have the flow rate 1 and flow rate 2. So the flow rate 1, you have the XA1. So in this case still, we have the M dot A in minus M dot A out. M dot A in, that means referring to the mass of A coming into the system, minus the rate of mass of A exiting the system. Since this case is just a blending, you mix the A and B, you don't have any reaction. So you don't have the rate of component I produced. You don't have the rate of component I consumed. So we just use the rate of component I in minus the rate of component I out. So for this part, we try to relate it. You have the dMA over dt. How to get the MA with the X? We know that MA equal to the XA multiply with the M. Where if we take a look, the MA here, kilogram A. XA, mass fraction, kilogram A over kilogram. Where the kilogram only is referring to the kilogram total, A plus B. And the M is your mass, kilogram. So when we try to multiply it, you get the kilogram A, which is you have the consistent unit for the left-hand side. So for this part, we can substitute into the given equation to become dxam over dt. So you have the dxam over dt equal to m dot a in. M dot A in is the mass flow rate coming into the system. Mass flow rate carry the component A. So you need to involve the F1 because it's the mass flow rate. And then in the mass flow rate, you have the composition. So you have the XA1. So if we take a look, F1 is the kilogram per minute. SA1 is the kilogram A over kilogram total. So when you try to multiply it, you get kilogram A per minute, which is consistent with the left-hand side. So this is the term to represent rate of component A coming into the system in the flow rate number 1. Since you have the second flow rate carry the component A, then we just add plus F2 XA2. So both is the represent flow rate of A coming into the system. Then we complete the rate of component I in. Next is the rate of component I out, which is F3 XA. So this is the symbol substitution for your term in the case of the conservation of component principle. What we need to do next is, if we take a look on the left hand side, you need to expand the equation. Where for this part, dSam over dt, we can expand it as a dm over dt plus m dxa over dt equal to f1 xa1 plus f2 xa2 minus f3 xa.
Doctor,
Yeah.
one question. Why the outlet is not SA3 and we consider it as SA only?
Okay. In this case, if we take a look, why the numbering is not consistent? So this one you can see SA2, SA1. All right. In this case, you need to be very flexible. In one way, of course, if we consider the complete numbering, it should be SA3. But sometimes you need to make sure you follow what has been given in the equation. So right now, for this part, the equation given is only SA. So we just follow what it is. Let's say the exit XA4, we need to follow it. That depend on the variable given in the question. Unless it is stated otherwise, then we can use the SA3, no problem. For me, in this case, if you put SA3, still okay, no problem, as long it's clearly indicated what is the variable for. So, in this case, SA is used to represent the exit composition. So I just use the SA. So you have the SA dm over dt plus m dxa over dt equal to f1 sa1 plus f2 sa2 minus f3 sa. So what to do next? If you recall, in this case, we have the dm over dt. And then you have the m. In the overall mass balance, we know that the dm over dt equal to F1 plus F2 minus F3. This is coming from the overall mass balance. The one that we developed before. And then we also know that the M equal to rho V. The relationship between the mass and the volume. So what to do next is to substitute the term inside the equation, where in this case we have the XA F1 plus F2 minus F3. So we have the dm dt, we substitute into this given question. Plus m is the rho density multiplied with the volume dxa over dt. Equal to F1 xa1 plus F2 XA2 minus F3 XA. So the next thing is to expand the given term. You get SA F1 plus SA F2 minus SA F3 plus rho V dXA over dt equal to F1 XA1 plus F2 XA2 minus F3 XA. So here you have two sides of the equation, on the left and on the right. So this part on the left hand side. So this is the LHS, left hand side of the equation, and the other part here on the right hand side of the equation, RHS. So once we expand the equation, the next step is to simplify or to rearrange your equation. So for this part, we will take a look. SAF1, this term can be factorized with this one. SAF2 can be factorized with the F2 on the right hand side. And then you have the similarity of the term. SAF3 and F3SA is the same variable, same term. Where if you have the same term, then that means you can cancel it out. So this part can be cancelled it out because both has the same term and the same sign, which is negative. So if you rearrange it, you bring it on the right hand side, it can be eliminated. So in this case, if we rearrange the equation, you have the rho V dxa over dt equal to F1 XA1 minus XA plus F2 XA2 minus SA. That's it. The SAF3 has been eliminated. So this represents the final component A balance for your case study.
Doctor,
Yeah.
one question. We know SA from the right hand side or left hand side. We know SA2 come from the derivation of the SA over the from the awal lah, the SA tu.
This one, right?
Yes. So we know SA2 come from that. But in the same thing, we know that we use F3 multiply with SA because we follow the questions. So does the SA from the F3 is same as the SA that we derive from the derivative?
Okay. All right. Okay, normally in this case, to answer your question, when we try to derive the thing, it is based on the boundary set for the equation. So for this part, if you take a look, the rate of accumulation, where the rate of accumulation coming in is coming from the inside, from this boundary. So it's quite clear. SA1 is supposed to be the flow rate in, SA2 flow rate number 2, and SA here referring to the exit flow rate. However, normally the XA in this case is located inside the liquid. Because you want to mix SA1, SA2. It is being mixed inside the tank. So during the derivation, we start the derivation based on this boundary. So it represents the XA. So for this part, this XA in the end will exiting the system through the flow rate number 3, the outlet flow rate. So we assume whatever composition inside is achieved under uniform composition. That's why you have a stirrer. When you have a stirrer, we assume it has the uniform composition throughout the liquid and it will exit the system. So based on this, based on our derivation, the XA represent the composition inside the tank. And we also assume the composition exit the system is equivalent with the composition inside the tank. So the answer is yes.
So throughout the studies, we assume it's always in the uniform.
Yes. That's why in this case, it's important to have the stirrer. So whenever you have the stirrer here, it will contribute to the uniform composition. So whatever inside will coming uniformly in the outlet stream. The same goes with the temperature. The temperature inside here, when you mix it, we assume the temperature become uniform. And the temperature inside will be equivalent with the temperature outlet. Normally, that is the normal assumption for the process control. So, any other question?
Doktor,
Ya.
kalau ni kan blending maksudnya dua stream input, satu stream output. Kalau yang satu input, dua output.
Okay. You mean that you have one input and then two output, like this?
Dia macam yang distillation column, ada distillate dengan bottom.
Alright. Okay. Thank you for the question. In this case, normally we will do it based on the unit operation. There are some scenario. For example, like this. This is what we call it tank. Only the simple tank. You have one coming into the system, but you have two outlet. So for this part, we don't call it mixing tank. This is not mixing tank. Not mixing tank. This is sometimes is mimic the storage tank. Or splitting tank. So the mixing, you mix together two different flow rate. For this part, one stream coming into the system and then you split into two. So you store it for a while, then you split it. So in this case, you don't involve any component balance. It just involves the overall mass balance. That is the first thing about the tank. And in some cases, if you have the separation, you have the distillation column. One inlet, two outlet. This one top, this one bottom. So this is the different phenomena because you separating the thing based on the, let's say, distillation column is to separate component according to the boiling point. This involve the liquid and vapor phase. So the thermodynamic is different. So when your thermodynamic is different, the derivation will also become different. Normally, we don't do the derivation of distillation column in this subject. Why? Because it is complicated. We just focusing on the tank only. Any other question? All right. So for this part, we have the for the first part, we have the conservation of total mass principle, where you have the d rho v dt. F1 plus F2 minus F3. So based on this, we already covered the overall mass balance and the component A balance. Why we need to derive this thing? If you take a look, this represents the dV over dt. So by solving this equation, we can predict how the behavior of your volume. In the end, afterwards, we will try to plot volume against time. So you can get the plot. So this is the function of this equation. In order to solve it, it will be covered later. First, we need to obtain the model. The same goes with the composition. So in the end, the outcome is we want to observe the behavior against time. This is what we call it dynamic. So let's say SA, the profile like this. How to get this profile? We will solve the given model. So this is the idea why we need to derive the mathematical model for this case study. So it's not that we will derive it without the purpose. There are purpose on derivation for both balances. So right now, we already developed two balance, the component A and the overall mass. Since the equation mentioned there are two components, component A, component B. Based on the question given for this case study, it is stated that two components are involved. For inlet stream, you have component A and B. For outlet stream, also you have component A and B. So now we already complete the component A. How about the component B? Do we need to derive it?
No,
Why?
No.
Why no?
because there's only component A.
Why there is only component A? If we refer back to the question, it stated that there are two components, A and B. If you refer back to the slide, each of the two feed stream is composed of two components, A and B. So my question is, do we need to derive component B in this question?
we need to derive it
No need, doctor.
Why we need to derive it?
because it's existed in the process.
Okay. In this case, there are two answer that is acceptable. The first one, you can derive it. Component A balance. How to derive it? The same way like you did for the component A. The same thing. So in the end, I think you will get the same answer like what you have for the component A balance. Only the different in terms of the labeling. Since we assume all of the component B is available in each stream, you may get rho V dxB over dt F1 xB1 minus SA plus F2 xB2 minus SB minus SB. So you will get the same arrangement like you have for the component A. Only the difference is you replace SA with the SB. That's how you can derive for the component A balance. A component B balance. Or that is the first solution. You do the hard way. You derive from the beginning, from the scratch. Or sometimes you don't need to derive it. Why you don't need to derive the component B? Any opinion?
1 minus XA equal to XB.
Okay, thank you very much. You need to understand the concept of the mass fraction. So normally this is the mass fraction. For the mass fraction, you have concept of XA plus XB equal to 1. Since you only have two components A and B. So once you obtain the XA, then you can obtain the XB easily, 1 minus SA. So you don't need to derive it. So this is the two way that you can adopt for the obtaining the component A and B behavior. So this is the important of the process understanding where the concept must be established. So any question regarding the derivation? You will see this kind of the derivation frequently. So this is only the beginning. So here, if you take a look, I straight away doing the derivation. Why? Because this is the concept. So I think you need to have the good exposure on how to derive this variable. So for the next class, I will show you how to derive the energy balance and how to classify the variable accordingly. So for today, before we end our class, any last question?
Doktor,
Yeah. Yeah. What is your question?
Nak tanya, kalau contohlah untuk test ke final exam kan dia nak XB punya composition, tapi kalau kita tak buat jalan kira daripada yang macam XA ni, kena tolak markah ke memang markah tu solid, just change label XA to XB?
Okay. Let's say in this case, normally, if you are certain how to get it, then you can substitute the symbol directly from SA into SB, no problem. Still, it will not have the mark deduction, no mark deduction for that. But you need to very you need to very sure. Is it the right? Is it that is the right way or not? The correct way or not? That is the thing you need to very sure before you decide on this thing. Or if you're not sure, then also you can derive from scratch. There are different way. Both are acceptable. Both have its pro and cons. Sometimes when you try to derive it, it will consume a little bit time. But if you did it wrong, maybe you can get some answer, some mark for it. There are pro and cons. This is the thing that I think we will explore it together. I will provide certain exercise for you to get familiarized during this course. Because here, if I try to explain it, maybe you're not very clear. Maybe later on, once we cover certain topic, we do the exercise, then maybe during that time, you will get familiarized on how to solve the given problem.
Okay, Doktor.
Any other question?
Sir, the test and final exam is open book.
Yes, open book.
Thanks.
Yeah, open book, open notes. Not only open book, but it's also open note. You can refer to any kind of notes. Because here we cannot evaluate, we cannot determine either you just refer the book or notes. So we just leave it open. Okay, if there is no further question, I sincerely thanks for your cooperation, for your participation. I'm looking forward for this kind of conversation. Feel free to ask. If you have something you don't understand, just ask me to repeat again or just ask me to explain again. Don't be shy, because here the key for understanding is to have a clear idea on what's going on. And how to know is it you understanding or not is by asking question. So thank you very much again for your participation today. I see you online again on Wednesday. With that, thank you and have a good lunch.
Okay, doctor. Thank you.
Okay, Akif.
Thank you, Doctor.
All right, everyone. Thank you. Have a nice day.
Doctor.
Thank you, doctor.
Welcome.
Thank you, Doctor.
Doctor. Thank you, Doctor.
Thank you, doctor.
Welcome.
Thank you, doctor.
Thank you, Doctor.